Today we're going to be talking about centripetal force. Yesterday we talked about centripetal motion. We defined uniform circular motion for an object traveling in a circular path having a constant speed but a changing direction, and therefore uniform circular motion is described by an radially inward acceleration. You can see on the picture here, you have an object attached to a string fixed in the middle. So the string maps out a radius and traces out a circle as the object rotates around. Yesterday we talked about how the period would be the time for one rotation, and the frequency would be the inverse of the period. How many rotations in 1 second? You notice here that if the string was to suddenly break, then the ball would fly off on a path tangential to the circular arc. And that's shown in the first picture. The other thing that you can see is that in the second picture is that the net force is in the same direction as the acceleration. And that net force and that acceleration are directed toward the center. They call this radially inward. So from yesterday we talked about this formula here, the constant speed formula, but it's the distance traced out is the circumference, so 2 pi r, and the time it takes to cover that circumference would be the period, capital T. So you have 2 pi r divided by t. Now we know from the last unit that the force is equal to ma, that's the net force. And what we can do is we can sub in where we see A, we can sub in our centripetal acceleration formula, v squared over r. And we get the force formula, centripetal force will be mv squared over r. Now there is a fancier version of this where you substitute the expression for v into mv squared over r. Apply the exponent laws, so 2 squared is 4, pi squared is pi squared, r squared is r squared, and then they just write the m at the end, no big deal there. All divided by, of course, t squared, as well as r is also in the denominator, so we end up with a t squared over r, t squared r in the denominator. One of these r's is going to cancel one of these r's, and we get this formula here. So essentially you have two options when you're given a centripetal force question. You can use mv squared over r, or you can use this 4 pi squared rm over t squared. Now as well, you can just solve for v separately and then use this formula. Like, this formula is not necessary. You don't always have to use this one. It's just basically, instead of doing two calculations, you can do it all in one. So these two formulas can be used to explain things like tension, gravity, and magnetism. We won't do any magnetism, that's done in Physics 30. But we will be doing tension and gravity, as well as one more, friction. We'll see how that relates probably in the next slide here. Now, there is a imaginary force called the centrifugal force that does not exist. It points radially outward. You can see the centrifugal force here pointing radially outward. This is a common misconception about centripetal motion. It's because if you're driving in your car and the driver makes say a left-hand turn, or looks like the driver's making a right-hand turn, in the animation, the passenger will slide out to the left. And this has more to do with Newton's first law, which states an object in motion will stay in motion. So watch the blue catches up to the red. And that's because the passenger wants to stay in the same motion, but the driver, who is holding on to the steering wheel connected to the car, is accelerating to the right, but the blue wants to continue going on a straight path, and they will intersect there like that. So it's more that the car intercepts the passenger rather than the passenger feeling this outward force. So this outward force is just a common misconception that doesn't actually exist. So there's no force pushing the blue person outward. The actual force is inward, the acceleration is inward, and then the blue person, because of inertia, will want to stay in the same path and then basically hit the person beside them. Alright, so this is in your notes package. I would definitely give this slide a read. These are probably the three main situations that you'll be interested in this course. So when a car is rounding a turn, it's the force of friction acting upon the turned wheels of the car which provides the centripetal force required for the circular motion. So here, it's the force of friction which points radially inward. For the bucket of water attached to a string spun in a circle, it's the tension force that is pointed radially inward. And for an object accelerating around, orbiting around a celestial body, so this would be like a satellite orbiting Earth, it's the force of gravity from Newton's law of universal gravitation which provides the force which points radially inward. So uniform circular motion can be described as the motion of an object in a circle at a constant speed. As an object moves in a circle, it is constantly changing its direction, and therefore it's undergoing acceleration. And in according with Newton's laws of motion, an accelerating object must be acted upon by an unbalanced force. This unbalanced force is in the same direction as the direction of the acceleration. So that just means that the net force points inward and the acceleration points inward towards the center for uniform circular motion only. And in Physics 20, you will only deal with uniform circular motion. The first image is basically it's a box with openings. So there's nothing for the tennis ball to catch up to. You can see in the second image, it's the exact same image, but there's a platform for the ball to catch up to. So essentially, a normal force is acting radially inward on the tennis ball, which will keep the tennis ball in circular motion. But if there's nothing there to supply the inward force, then the tennis ball will just continue on a tangential path. Okay, so this question is going to be about an ancient weapon, which is essentially just an object attached to a string, and then it's whipped around in a circle and then released. So it's basically a projectile after it's released. So it says, well, how much force is required to spin a 2.5 kilogram, looks like a rock, at a velocity of 15 meters per second if the rope is 75 centimeters long? So from previous slides, we know that the centripetal force is equal to mv squared over r. Now, if you look at the information given, we essentially have everything that we need to solve for the centripetal force. So 2.5 kilos multiplied by the 15 meters per second squared. Pardon me, just 15 meters per second, but the whole quantity is squared. Divided by the radius. And I noticed yesterday in your guys' homework that some of you were forgetting to convert the centimeters, so that would be 0.75 meters. Okay. So just like before, you have to have your standard units, 2.5 kilos times 15 meters per second, square that value, and then divide it by 75 centimeters, which is 0.75 meters. And you get 750 newtons. And forces are vectors, so you need direction. So it would be radially inward. So the force required would be in the string. It would be a tension. So essentially what you have is F net is equal to the tension. And for F net, because tension is the only force acting, so the sum of all forces, there's only one, and that's T, acting on this object. And then for F net, for circular motion, we put mv squared over r is equal to T. So what we just solved for is the tension in the rope. This is the tension in the rope. So the F net equal to ma from the last unit, now instead of subbing in, what we would always do is sub in m. What we would always do is sub in ma here. We do a special case of F net. So this is the special case for centripetal motion. So rather than subbing in ma, we sub in mv squared over r for a uniform circular motion. So we have a sled attached to a pole moving in a circular path, and it must have been given an original push before, and it's on a frictionless ice surface, so this is an idealized situation that's just going to go on forever. So a sled with 25 kilogram mass is resting on the horizontal sheet. It is attached by a 5-meter rope. So the radius is 5. Once given a push, the sled revolves uniformly in a circular motion around the posts. If the sled makes 5 complete revolutions every minute, find the force exerted on it by the rope. So we can deal with that first. 5 revolutions every minute one of the hardest things in uniform circular motion is deciding whether the time given is in a frequency or is a period. So this 5 revolutions per minute is a frequency because the time is in the denominator. That's crucial. So essentially you're doing 5 revolutions every 60 seconds. You have to convert to your standard units, minute to second. 5 divided by 60 is 0.083 repeating, and we can put revolutions per second, or in other words, 0.083 hertz. So we've solved for the frequency. We take the reciprocal of the frequency, and we get the period. So we're going to take this value and take the reciprocal. So you have to invert it. And you get 12 seconds per cycle. So in essence, just 12 seconds. So we've solved for t, the period, which is the time to complete one revolution. Now we're asked to find the force exerted on the sled by the rope. So the force is along the rope. I'm going to call this the force due to tension. I'm not going to just call it capital T because I'm calling capital T period. So this is the force due to tension. Now if I was to draw a free body diagram on that sled, the weight of the sled points down, so Fg points down. The ice surface provides a balancing force upward as the sled is not accelerating vertically. It is, however, accelerating radially inward. So depending on where you are along the path of the circle, there will always be a net force pointing inward. And that net force is the force due to tension in the string. So we say here F net is Ft. We're not interested in the vertical stuff. Those guys in a sense cancel out, equal and opposite. And F net has a special case for centripetal motion. So we say Fc equals Ft. Okay, so Fc, the centripetal force, is the force in the string, the tension force. And we can sub in for Fc mv squared over r. It's the exact same process as the last unit, but instead of putting F net equals ma, we put Fc equals mv squared over r. And remember that Fc is the net force. And the net force is the sum of all forces acting radially inward. And there's only one force. So we have the mass. (25 kilograms). But we don't have the velocity. We know the radius is 5, so all we need to do is find the velocity, and then we can solve for this force due to tension. So from before, we know that the velocity is 2 pi r over t. So 2 pi times 5 divided by 12. So we get about 2.6 meters per second, which we can sub down here. Don't forget to square it, and we'll get the force due to tension. So 2.6 squared times the 25 kilos divided by the 5 meters. And we get 34.3 newtons for the force due to tension. And this, of course, acts radially inward. So evaluate. A greater force would be needed if the sled moved around the circle at a higher speed v. In fact, if v were doubled while the radius remained the same, then the force would be 4 times greater. Can you show this? So we know that mv squared over r is the formula for the centripetal force. They're going to tell us that the velocity is doubled. So the new force, Fc prime, will be m in a bracket 2v all squared over r, as the mass and the radius are staying the same. When you square that bracket, you get a 4. 2 squared is 4. So you can bring that 4 out to the front. And this was the original force. So you can see that it's 4 times greater the original force. As a challenge, you can try the last one. How would the force change if the velocity remained the same, but the radius were doubled? So the mass and the velocity will stay the same, but the radius is doubled. What's going to happen to the force? So that's a challenge for you guys to do on your own time. So this next question is very common and very likely to show up on your exam. I'll put a star on this question. It's about a vehicle making a circular turn. So essentially, it's just a vehicle moving along a circular path. It's just a vehicle making a turn. So if you were to have a different view on the vehicle, the free body diagram would be as such. Force gravity points down, force normal points up. And if I'm turning to the right here, then I would need an acceleration that points to the right. So I would need a force that points to the right. And when we're talking about vehicles making turns, then the force that supplies the radially inward acceleration is the force due to friction. We're given the coefficient of static friction, and that implies that it's not sliding. Now we live in Canada and we're used to slippery roads, and you can probably remember being in a vehicle that when you make a turn on a slippery road, like maybe if there's ice or something, that the car will start to slip and start sliding. That would be kinetic friction. That would be the friction during a slide. But for this case, the vehicle is maintaining the radius of curvature. It's not sliding off, going to do a spin out. So it's the friction static that maintains the radius so that you complete the turn in a circular path. So when we look at the F net equation, the sum of all forces acting radially inward, where there's only one. So the net force is the force due to friction. So this is what we would have done in the last unit, but because it's a centripetal force, when we substitute in for F net, we substitute in the centripetal force, which is not ma. Well, it is ma, but written in a different way. It's mv squared over r. So we put in the centripetal version of the net force, which is mv squared over r, because this is just a. V squared over r is just a. Now the force of friction, we know from the previous unit, is mu Fn. And by taking a look at our free body diagram, you can see that the force normal, of course it's the upward force perpendicular to the surface, it's equal and opposite to Fg, so we can sub in where we see Fn, we can sub in for Fg. Let's move this up here. We have mv squared over r is equal to... Alright, so we can substitute in where we see Fg, we can just substitute in the formula for Fg as mg. Now looking at the left side and the right side of the equation, we can see that there's a mass on both sides, so we can cancel the masses. And then they're asking us to isolate for the velocity. So we can take that r downstairs on the left, upstairs on the right. We get mu times g times r. And then of course we can square root this to solve for v. So 0.7 multiplied 9.81 multiply the radius 25. And we get 172 roughly meters per second, which needs to be square rooted, and you get 13.1 meters per second. Now I'm just going to times this value by 3.6 to get the kilometers per hour. And it's about 47 kilometers per hour, so about 50 kilometers per hour. Now I want you to think about if you were taking a turn with this radius, it says maximum safe velocity. So most of the time, if you're a smart driver, if you're a careful driver, you're going to take turns, at a slower speed. Because if you go any faster than this 13.1 meters per second, or about 47 kilometers per hour, you're going to slide. You're going to slide and spin out. So again, this is a maximum velocity. The truck doesn't have to go this speed. It can go lower than this speed, but this is the maximum speed it can go before sliding out. Then once you start sliding, it's a different physics problem and it becomes kinetic friction, and yeah. But yeah, this example here is very common for the centripetal applications. So big star on this question. So these questions here are similar to the evaluation we did a couple slides ago, where you have to rank them in order of largest to smallest tensions. So largest to smallest FC. So it's the largest centripetal force. So in this example, you have the force being mv squared over r. And then the next three, you have to see what happens if you double the radius, double the mass, or double both. So I'll do one of them for you. I suggest that you practice this as well on your own. I believe I did double the speed, so this will be okay. So let's go Fc prime, as this is going to be a new force, but we double the radius. So we have to replace r with 2r. Okay, so if you slide out the coefficient 2 in the denominator, you can see that that's going to be exactly half of the original force, as mv squared is the original force. So for this example, if you double the radius, it'll be half the original force. What happens if you double the mass? So Fc prime would be twice the mass, v squared over r. If you slide the 2 out in front, then you can see that it's going to be 2 times the original force. So this will be double the original force. Double the original force. Okay, so if you have it, and I hope this makes sense, you have a larger mass, you're going to need double the mass, and you're going to need twice the force to supply the same radial path. I'll leave this last one for you guys. And here's the homework for section 2.